But before that, just first going to show you the steps involved in publishing a message in a couple of simple cases. So this looks very similar to the very first diagram. We've got a producer and a consumer communicating with each other. Inside the box, we've got an exchange and a queue. And you might ask, well, how did these things come to be here? So AMQP, in the same way that SQL lets you define tables with the create table statement, AMQP lets you declare exchanges and queues. So it's possible in this case that a producer declared an exchange and the consumer declared the queue and declared the binding. And that's how this picture came to be. It's entirely possible to set this up ahead of time as well, but AMQP is general enough to create the configuration and to change the configuration of the broker on the fly. Publishing a simple message on this side, we've got a producer wanting to send a message to my exchange. In this case, the type is fan out. I'm going to show you the different kinds of exchanges later on, but this could be fan out or a direct exchange, in fact. As soon as the message is sent, it ends up in the queue. A second message might end up in the same queue. As soon as a consumer consumes that message, it's removed from the queue, and the same with the second message. So that's a straightforward, dead simple, straight through publishing and consuming scenario. The next most complicated example is when there are more than one consumer connected to the queue. In this case, the multiplexing is happening at the queue. So we are going to have as many messages before publication as we have after consuming the messages. So messages weren't actually duplicated in this case. It is possible to duplicate messages, however, in the case of a fan-out exchange, and this is where the distinction between a fan-out and a direct exchange becomes important. In this case, messages are going to be duplicated into both MyQ and MyQ2. If we've got 3 messages to start with, we're going to have 6 messages afterwards, and those can be consumed from the queues at different rates. Two consumers, in fact, of MyQ might be faster than the consumer connected to MyQ2, in which case MyQ2 is on average going to be longer than MyQ. Rabbit has features, is able to actually grow queues pretty much to the limits of how much hard drive space you have. So if some of the queues become too long, they'll be automatically flushed out to disk, so as not to impede the flow of messages to faster queues for consumers that are able to keep up. And the most complicated example that we're going to look at is topic routing. So in the previous example, we had a fan-out exchange. In this case, the exchange is a topic exchange. What that means is that consumers are able to express an interest or subscribe to messages matching a certain pattern by declaring a binding with that pattern. And producers, in this case, send messages with a routing key that gets matched against that pattern. So this is an example of implementing logical separation, where logical decoupling, where producers don't know anything about consumers, or in fact whether there are any consumers at all. So in this case, the consumers of MyQ are interested in messages that end with E and that have 0 or more words before the E. Consumers of MyQ2 are interested in messages that have an A at the beginning, something in the middle, and a C at the end. And we can see that message A is not going to match any of those patterns. So the question arises, what happens to that message? By default, it will just get dropped on the floor. But AMQP and Rabbit has means for defining alternative outcomes for that situation. The producer could be notified, or it's possible to define a default action for unroutable messages. The next message is in the same category. It doesn't match anything, so by default, it's just going to be dropped. C matches the first pattern because there's an A at the beginning, a C at the end, and something in the middle. So we expect C to end up in Q2. And the last three messages all end in an E, so we'd expect these to end up in the first queue, which is exactly what happens. So this was a simple run-through explaining how publishing works in a couple of basic scenarios. In order to understand that, we needed to define a number of different exchange types. We saw there an example of a fan-out exchange, which duplicated all the messages, and a topic exchange, which defined patterns that bindings use to match and route on the grounds of topics. There are two other exchange types defined in AMQP, and that's a headers exchange, which routes on the basis of message headers, and a direct exchange, which doesn't do any routing at all. It just forwards on message as is. The other major nouns in the AMQP model is the queue, and queue properties are passive, durable, exclusive, and auto-delete. Passive queues, declaring a queue as passive basically just asserts, is a way of checking that that queue exists. A durable queue is one that will continue to exist after the broker restarts. An exclusive queue is one that only one consumer is able to be connected to. An auto-delete one is the one that disappears automatically as soon as all consumers have disconnected from it. And an exchange shares many of these properties. So a passive exchange is a way of declaring an exchange as passive, is a way of checking whether it's there. If it's not there, it's not going to be created. And if it is there, it will throw an error. A durable exchange is one that's going to be persist after after the broker gets restarted, and an auto-delete one will disappear as soon as there's no one else connected to it. So next up is a list of prominent AMQP implementations. Now, not all of these projects are equally active. In fact, some of them are completely inactive. But the point that I wanted to make here is to show you that RabbitMQ is the only example that's written in a language that's not imperative. So you can expect the code bases for these different implementations to look very, very different. And next up, we're going to look at some of the properties of Erlang that makes it an ideal language to implement a protocol. It's extremely concise, and I'd say this is probably the most important feature. It's possible to express for example, the specification XML that I showed you earlier on, to express that in a very, very small number of lines. And what we end up with is a relatively small code base. The concurrency model is ideally suited to a project of this nature. Erlang doesn't have any shared state at all, so all of the locking and the semaphores and the problems that plague large code bases that try to solve a similar problem simply don't exist in Erlang. The concurrency model is what's called process-orientated, so threads are extremely lightweight, and it's simple to spin up as many as you need, and RabbitMQ certainly makes use of that very heavily. It's got a built-in distributed database called Amnesia, which we make use of in order to implement clustering, and it's multi-platform. So it abstracts away all of the things that might make it difficult to implement a complicated software system on different platforms. So most flavors of Unix and Windows and any potentially into the future other architectures, RabbitMQ can be made to run on. So here's an example of the binary matching that I was talking about earlier. This is the code that was automatically generated from the XML specification I showed earlier. So what this says is everything between the double angled brackets here is a blob, so that's a binary chunk. And it says break this up in a way that defines variables f1 to f0 to 3 according to this pattern. So give the first 16 bits, call that f0, call the next 8 bits f1 len, and then use as many bits to define f1. So the interesting thing is to notice that f1 len is assigned here and it's already being used right here. If you had to implement something like this in another programming language, it will take quite a bit longer to express this idea. So what is RabbitMQ? It's an AMQP implementation to start with. And it consists of a broker running on port 5672 and several clients. So there's a Java client, a .NET client, and a number of other clients written in other programming languages. And the clients and the servers speak the AMQP protocol to each other. And RabbitMQ consists of the broker as well as those clients. Because AMQP is an open protocol, anyone else can implement a client as well, and many have done so. For this audience, the Spring client, I think, is of particular interest. So there's a Spring AMQP implementation, which is probably the simplest way to go about transitioning your application from JMS if you're using JMS. It's in lots of popular Linux distributions, and it's very easy to get going on Mac OS and Windows as well. And it's released under the Mozilla public license. It's a relatively small code base. It supports clustering, so that you can use multiple machines to help share the load of a big problem. And it can be made to work with Pacemaker to give you high availability in a data center or in an environment where it's absolutely crucial that your message broker runs 24/7. So that's another property of Erlang, which makes it ideally suited, that Erlang has very, very high reliability, and systems providing 5 nines of reliability have been created using Erlang. And Rabbit has a number of extension points via plugins. So if you have an exchange scenario where you, for example, have a great idea to route XML messages based on, for example, XPath, you can go ahead and implement your own exchange and plug that into RabbitMQ. Or if you've got a good idea for a backing queue solution, then you can plug in your own queue storage. And that has been done by some. I know that there is a Tokyo Cabinet plugin for backing queue storage, for example. Rabbit was conceived originally as an AMQP broker, but it has moved beyond that label, I think it's safe to say. In that it offers as plugins or as bridges or as adapters support for other protocols as well. And in the future, we see that as a growing trend. It first and foremost does support AMQP together with SSL to provide confidentiality. But it also supports STOMP, and cases where you might consider STOMP is if your particular language doesn't have an AMQP implementation yet, or if you're in an extremely resource-constrained environment. STOMP is a very good, there's a very good chance that you'll either have a STOMP client already, or you'll be able to create one very easily, because STOMP is very similar to HTTP. It lacks a lot of semantics, but it's very, very simple to get a client going using STOMP. XMPP you might consider if you want to interoperate using that protocol. And there's a bridge for 0MQ as well. So 0MQ is a completely different protocol which is brokerless, so it's able to operate without a broker, and it's possible to have Rabbit act as a node, take part in a rmq conversation.